Welcome everyone, and thank you for attending our webinar today on building a live fraud dashboard. My name is Greta Workman, Marketing Manager here at Neo4j, and I'm joined by Jesús Barrasa, Field Engineer at Neo4j, and Matthias Korn, Head of Solutions Engineering at DataVirtuality. We are so excited to bring you today's presentation. Just a few housekeeping items before we get started. We invite you to submit any questions at any time throughout the presentation using the questions box of your GoToWebinar control panel. We'll answer as many as possible live at the end of the presentation, so stay on for those. Lastly, an on-demand recording of the session will be made available, and the slides will be made available for you to view at your leisure. Keep an eye out for an email with both of those links, either probably tomorrow or later this week. All right, well with that, I'll turn it over to Jesús.
Great, thank you very much, Greta. Can you hear me all right?
You sound great.
Good, excellent. Right, so yes, here we are. So my name is Jesús Barrasa. I'm part of the field team, as Greta said, and I'm joined today by Matthias. So we'll be talking today. Let me introduce the agenda very briefly about how these two technologies integrate together. One is graph databases with Neo4j, and the other one is data virtualization as data integration technology. And we're going to use that in a very particular use case, which is one of our key use cases in Neo4j, which is that of real-time live fraud detection. So what we're going to build, or at least go in a bit of detail on, is in the construction of a live dashboard for fraud analysis that involves data integration, as we will see. We will start with a brief introduction of the two technologies and then dive into the construction of the dashboard. We'll finalize with some takeaways and open the session for Q&A. Right. So very briefly, what are graph databases? What are graphs? I mean, since you've joined this session, maybe some of you are already familiar with Neo4j, but graphs are just a way of representing data, and Neo4j is the world's leading graph database. So what do we mean by representing data as a graph? So for a very long time, I mean, we've been representing data in tabular format, which has worked reasonably well. And the reason for that is that data has been very predictable, very boring, if you want, for quite a while. So data was collected through forms and was used for reporting, and that works very nicely with tables. But the thing is, these days, data is less predictable, much less predictable. Is very variable. Is very heterogeneous. So you will get different data structures, different richness of data if you get data from a customer through a mobile device, or you get it from a desktop one. So I mean, this assumption that relational would be the right solution, it's not valid anymore, and that's where the whole NoSQL initiative has came a few years ago. But let me quickly introduce what this notion of graph thinking is. So let's take this simple example. We have a set of transactions. Think of money transfers between individuals. That's a simple Excel spreadsheet where we have the sender, the receiver, we have the amount, we have a timestamp. So it's the simplest data set that you can think of. So the way we've analyzed this data for a long time is doing charts, doing histogram, pie charts, etc., etc. So we were grouping individuals and finding which is the biggest receiver, the biggest sender. Fine, for that, tabular is great. But let's now swap our lenses. Let's look at it from a different perspective. Let's look at data as a graph, and that's exactly the same data set but loaded into Neo4j. So what we see is the data starts kind of talking, starts showing us how, for example, something that was not obvious from the original data set, that we have two isolated sets of users, right? We find clusters. We find individuals that are the bridge between different communities. We have a new set of potential analysis that can be carried out in a graph. So this change in the mindset is what we mean by graph thinking, and that's what graph databases and Neo4j in particular will enable. So very briefly, what are the basics of the property graph model, which is the one that Neo4j implements? A graph in any kind of graph will be formed of two main components, which are nodes and relationships, right? Nodes are entities, are concepts, are individuals that are related to other individuals through relationships, and these are basically the two main components of the labeled property graph. A node is a structure, as you can say, that can be labeled, can be categorized. In this case, we have the two top nodes labeled as persons, and the one at the bottom is a car. And they also can have a set of key of properties, right? That are basically a set of key value pairs. So for an individual, we can have a name, the date of birth, the Twitter handle, which doesn't need to be the same as for every other individual, and that's the idea that I was mentioning before. So we don't have to impose in a rigid manner what data has to look like. So a graph is schema implicit, if you want. So it can take data, can ingest data in a very natural way, even if that data is reasonably variable, as this is the case. So yeah, first element, nodes representing the entities with attributes that characterize them and labels that can group them by role. And the second component, of course, is relationships. Relationships are directed. They connect two nodes, and they can be typed. They will have in our case, we have the loves relationship that connects both Dan and Anne here. We have the lives with, and we have the drives that connect individuals with other individuals. And interestingly, we can also add properties to these relationships. So we can add to a relationship its weight, which is a cost, for example, something that's extremely useful where you think of graph analysis like path, shortest path, cheapest, or less costly path analysis. So adding the things like a timestamp, like the cost, like the weight of a relationship is extremely powerful. So this is the labeled property graph model. These are the basics. So it couldn't be simpler and more intuitive, but still very, very powerful and expressive. And there's not a single domain that can be modeled according to these paradigm, to this model. So if we compare with relational and with index-based approaches, we are kind of moving, and now we're talking a little bit more into how data is stored and not only modeled. We're moving from a space where we have been using the notion, for example, of foreign keys and indexes to connect elements. Think of a many-to-many relationship in the relational database. It has to be modeled through a join table, which is not the most intuitive way of doing it. And not only it's not intuitive, it also introduces problems like performance and maintenance cost. Right? Think of the queries that you have to build when you start building a model like that. So we're moving from this way of representing data to a more natural one, where we have explicit connections between nodes, and something like a many-to-many relationship is a natural thing that's stored in disk in this particular way. Right. So while graphs are very visual things. I mean, it's a structure that lends itself very naturally to visual exploration. The interesting thing with Neo4j is that you can not only model it and explore your graph, but you can also query it in a very powerful way. And we use for that the Cypher query language. And the Cypher query language is based on an ASCII art. Basically, what we're doing with this, and this is a fragment of Cypher, we're kind of drawing the patterns that we're looking in our graph, we're looking for in our graph. So in this match expression, which is like, asking the engine to find this pattern, we're looking for a node that's represented by the parentheses of type person that is connected through the loves relationship to another node, also of type person, first one with value Dan for property name, and second one with value Anne for the same property name, right? So it's a pretty express. I mean, I'm not going to go into the details of the Cypher query language. Is a complete language. You can do aggregates. You can compose patterns and transformations. But the idea is that it enables you to express the patterns that you want to find in your graph in a very natural way. So just very briefly, Neo4j is a data store, so some of the key features that you would expect from any store are present in Neo, and the main one I probably have not emphasized enough on it is the fact that that Neo4j is a native graph store, and that means that it stores the data. It's not a logical layer that exposes data or presents data as a graph on any other kind of backend storage. It actually stores data natively in disk as a graph, which means that it persists the connections between nodes and moves from a place where you have to scan indexes to one where you have to chase pointers, which is something that computers do in a very efficient and fast way. So that makes it adequate for real-time solutions like the one we're going to explore today. As a scalable store, it can be deployed in high availability configurations in clusters. It's ACID compliant, so if data integrity is important to you, Neo4j is a great solution. And you will be able to interact with Neo from any programming language through a number of drivers that are, some of them official, some of them supported by the community, making it really easy to interact with Neo. Right, so just to conclude, we find Neo being used in every single industry, so from finance to healthcare, telco, retail, and in some of our key use cases, which are fraud detection, which is the one that's going to be the main topic of today's session. Things like real-time recommendation, entitlement, root cause analysis. That's typically a telecoms space one, and graph-aided search. Right, let me hand it over now to Matthias so he can do a brief introduction of data virtualization.
Yeah, thanks, Jesus. Can you hear me well?
I can hear you very well.
Okay, thank you. Yeah, so let's take a look at data virtualization and data virtuality as a product. So I'm moving to the, Jesus, can you move to the next slide, please? Because I think I lost. Yeah, I'm requesting keyboard and mouse control again. So it should be coming up. Yeah, now I have it. Okay, so let's take a look at the definition that was put up by Gartner last year about data virtualization, and also the logical data warehouse is something that Gartner, by the way, sees as a very important aspect of data integration, also for the BI atmosphere. So let's take a look at this sentence here. So data virtualization technology can be used to create virtualized and integrated views of data in memory, rather than executing data movement, physically storing integrated views into target structure, and provides a layer of abstraction above the physical implementation of data. So this is a very long sentence. Let's take a look at the, especially at the back of the sentence. So we provide a layer of abstraction above the physical implementation of the data. So it doesn't matter if you have a tabular structure in your data, if you have CSV files, a web service, a NoSQL database, so unstructured data, all of this will be abstracted with this layer of abstraction from data virtuality, meaning we can access all of these data sources using one SQL language. So as a user of data virtualization and also our product, you will only need to learn SQL, and all the implementation details, all the technology details will be hidden from you. So that's this part. The other part is the virtualized and integrated views. This means that I just structure the data in a view, and I can change this view very quickly. So this is more or less just a SQL statement, just a select statement. And since I don't have to physically move the data, I'm much quicker, I'm much more agile, because I can change the views very quickly. So that means I have a high agility. I don't need to learn the details about the implementation of the data sources or how to query them efficiently. And let's now take a look at the foundation of data virtuality. So there's, apart from data virtualization, and data federation in that case, so meaning the ability to query two different data sources, but executing, for example, a join or a union in memory. So this is one part of the foundation. And the other part of the foundation is our self-learning analytical database management. This means we keep track of how people are using it, of how people are using data on our server, and we build statistics on that, and we recommend what data to ingest. So basically, you still have your live access, and whenever there's data too slow or historical data comes into play, you can materialize this into some analytical database. So you have a high query performance for the analytical queries, but at the same time, you can still bring in real-time data from the virtualized data sources. So with that being put together, you will always have real-time data with high performance, which is a very large advantage over ETL solutions, where you would always need to move the data into a central repository and then keep it there. And whenever some structure is changing, you need to change the whole structure and need to rerun all your ETL tracks again. But with data virtualization, you just rescan the metadata of the data source, and then you're good to go. Also, the same applies for the business logic. So the virtual views, the integrated views, you can change them in real time. So let's move on here to the next slide. Let's take a look here at the structure of the data virtuality server. So we can see that we have on the left-hand side all the different data sources, very many different types of data in terms of structure also. These are just examples. So right now we have more than 150 connectors to different systems. And with all these different connectors, we can connect a variety of these data sources. And as soon as you connect them from the data virtuality server, they are immediately integrated. That means you can create your queries across different data sources, and the server will join this data together in memory, meaning I have real-time data, and also meaning I don't have to worry about changing structures, because I can always, as I said, rescan the metadata. We have the data virtuality server here in place, and on the right-hand side, we have the BI front-end tools. And you can see that data virtuality server acts as a database, as a virtual database for our BI front ends on the right-hand side. So if you use your BI front end, such as Tableau or Looker, and also a variety of other different systems available, you can simply drag in tables from all kinds of systems and put them together, and the server will always take care of preparing this data for you, of joining it in real time, and also analyzing how people are using it, and in that respect, providing the opportunity to materialize the data into the analytical storage, which we see at the bottom of the data virtuality server. It can be one of those systems, and some others as well. Some key aspects here are as well that the data flow can be in two directions. So we can also write to data sources. We can write back to data sources, which would lead us to the scenario of retrieving data, analyzing it, and putting the result into another database, and writing the results there, and therefore acting on the data that we have at hand. So let's take a look at the next slide. And let's take a look at the benefits and summarize a little bit of what we've seen. So it's not only benefits of data virtualization, but also of data virtuality as a product. So on the left-hand side, we see you get all the information, no matter if it's a high volume of data, for example. We do, for example, push downs of predicates, meaning if you put a where statement into your query, only this data will be gotten from the data source. So even for high volumes, it's still possible to access it using data virtualization. No matter what structure your data has, we can access this. We put our own structure onto it, always a tabular structure, to make it joinable and to make it look like a relational database system, also from your BI front end. And you can go back to focusing on your business needs and not having to worry about the implementation, having to go to the IT department to write some queries for you or fish data out of the data lake. You can focus on your business needs and specify them in the virtual views, and DV will provide the data for you. The data integration is smart, so it's a low integration cost because in terms of personal, we're good to go in 2 days for some scenarios. So you don't need to worry about large project times, which in large companies go for months, according to Gartner, for months, and still fail, have a high failure rate. You have real-time access, which will give you an advantage over other businesses as well. An agile setup, and the business outcome will be improved as well. You have a fast return on investment because the data will be flowing very quickly, which is the same, of course, for different data integration scenarios, but here it's faster than the others, so it's state of the art. The projects can be finished in days, so we really had a project proof of concept running for one customer, and we could provide the same insights to the dashboard in 2 days, where a consulting firm took 2 months to work with this. So it's really makes a difference in terms of agility and time frame. And of course, you get more business insights, so you can ask the right questions, get answers, go ahead of the competition, and the IT is kind of freed from having to provide data for you. So the IT guys can also go back and focus on their IT stuff, because the technology of data virtuality will take care of integrating all your data and providing it for you. Okay, so that's it for the Data Virtuality product. So let me know if you have any questions, and I get back to Jesús.
Good. Yeah, thanks. Yeah, you probably can pose your questions as we go, and we'll open some time at the end to try and answer them. Right. So you have now an idea of what the two technologies are, and now we're going to dive a little bit into the scenario that we're going to describe today, which is this fraud analysis case. So just before we go ahead, just what kind of fraud are we looking at? So if you're familiar with fraud analysis, typically the most straightforward approach is the analysis of data in order to try and find outliers, right? Outliers are transactions, are individuals that fall outside what's the expected range. Things like transactions that take place outside the expected geography. We've all been in this situation where we travel abroad and our credit card or debit card gets blocked because you're using it in an area that's not the one you use it normally. So this is easy technically, but the problem is it generates a number of false positives. And it's not the kind of analysis, this discrete analysis that we're going to be looking at with Neo4j, with graphs. The one we'll be looking at is one a bit more sophisticated, which is related to structures rather than individual outliers. So we're going to try and find unusual patterns in our data that don't necessarily fall outside the predicted, expected range. So they're not outliers, and we'll see that the specific case we'll be looking at is precisely fraudsters that try to pretend they're normal, but that require this structural analysis that will be possible with the graph, as we're going to see. So what's this case? Let me describe this idea of a fraud ring. So if you look at the top right diagram, this schema describes 4 individuals. So there's a number of individuals involved in this type of fraud, which have, of course, each of them have their own means of identification. They have addresses, they have phones, they have social security numbers, etc., etc. And what they do is they generate synthetic identities. They generate fake individuals by combining these elements, right? And they use these fake individuals to open bank accounts. And these individuals can behave perfectly in a perfectly normal way. They can interact with the bank. They can be perfectly within the ranges, not be outliers at all, and at some point qualify to apply for a line of credit. And it's at this point where they get this line of credit that they just disappear. And then, of course, an investigation starts, but these individuals just don't exist. I mean, the investigators will go to the address, but in the address does not live that person. They will use that phone. I mean, and this kind of fraud is not something that we can identify applying this approach of outlier detection, because precisely what these people will try to do is cultivate the account, make it look as if it's normal, in order to be able to apply for these lines of credit. So what we'll need to do is try to analyze it structurally and find unusual connections. Things like, for example, if this individual has an address that is the same address as this other individual. And while that can be normal in some cases, because people live together, of course, we will find less usual patterns where one is sharing address with another one, but sharing phone with a third one, and this one is sharing social security number with a fourth one, forming in some situations a ring like the one that's described here, that's completely abnormal and is a potential fraud scenario. So that's the kind of thing that we're going to be able to model and query in a very natural way with Neo4j. We have a similar one below that applies more for the insurance industry, where we find claims that are each of them normal and not outliers again. But if we analyze them structurally, we see that another type of fraud that happens in the insurance industry is that we have fraudsters that appear once as involved in an accident, sometimes as witness, sometimes as passengers affected by and it's only when you look at the role they've been playing over time that you find very, very unusual patterns. So that's another similar one. But let's focus on the one about fraud rings, because that's the example we're going to use in our demo. So what do we have? So we have, let's assume we have this fraud detection platform built in Neo, and what happens is that that fraud detection platform is up and running and is picking up fraud as it happens, because as accounts are provisioned, we will be detecting rings and reporting them and acting upon them. We will find groups of users that will want to benefit from this graph as well, but they will want to eventually integrate that data with data coming from other systems, and that's precisely the case we're going to describe today. And so we will find ourselves in a situation where we will want to integrate data to provide unified views, and that sometimes will involve data coming from the Neo4j graph, and we will be able to support different types of workloads. So as I was saying before, we will be able to in an automated way detect fraud and report or act upon it. But at the same time, we want to be able to use the data in the graph and these fraud rings that are detected, and by integrating them with data coming from other systems to provide data for more analytical dashboards, which is what we're going to see today. So what are the elements in the solution that we're going to see? So we will have a Neo4j graph database that models the data that I've described before, and that's detecting rings, fraud rings. But we will have also let's think of any relational database that's at the back end of a CRM system. But we will want to bring these two together through, and that's where data virtualization, data virtuality comes into play, through by integrating them and present it as if it was a single unified source to analytical users. So there's a group of users that are probably less technical, that just want to have access to a unified view of the data, and they want just to be able to plug in their favorite BI tool, whether that's Tableau, Click, Excel, you name it. So that's the demo that we're going to show today.
So what does this look like for real? Let's jump into the demo. Okay, what you're seeing in front of you now is Neo4j's browser, right? This is the developer's environment where you can query the graph, where you can visualize, where you can interact with it, you can modify it, and it's currently preloaded with some customer data, some customers' accounts, contact details, etc. But keep in mind that this is a live data store. So as accounts are provisioned, we'll be bringing them into the graph. And what does our model look like? Let me bring up some nodes. Okay, so as you can see, we have a number of account holders, and for each of them, we have a set of elements that relate to them. For example, their social security number, their bank accounts, the products that they've subscribed to, their addresses, their phone numbers, and well, that's our simple model. But as I was describing before, probably here, well, it's not a very frequent pattern so far, but what we expect to find at some point is some matches, some rings. So, for example, things like these two individuals sharing address, or maybe sharing phone in an unusual way. So that's what our model looks like. Okay, and well, the kind of logic that will be running on Neo are cipher queries like this one. So let's very quickly look at it. We're looking for two account holders that share some contact information. It's a very simple pattern, but if we run it, we will see that the engine returns a nice ring involving 4 individuals: Amira, Amparo, Amina, and Amy, which share addresses, phone numbers, social security numbers in a quite unusual way. So I wouldn't be surprised if there's some fraud involved in this configuration. So yes, this is the nice visual representation that we can see when we explore the graph. But keep in mind that what's happening behind the scenes is that this front end, the browser, is actually sending, and we can have a look at what's going on. It's sending a request using the Vault protocol, sending a request containing the query to the engine, and the engine is returning the information in a structured way. So it's a JSON structure basically that then can be consumed in an automated manner. And I bring that up because even though it's something quite nice and intuitive to see, we have to think that as I was saying, the graph is a live thing. So accounts are being provisioned, and these kind of rings are forming over time. So what we want to do is in an automated way and in as much real time as possible, pick these up and act upon them. So we can think that there will be a process that's monitoring every time accounts are being provisioned in a sort of trigger way, or even polling the graph for patterns like this one and acting upon them. That can be raising an alarm in a fraud management system. It can be sending an email to the responsible person. It can be any kind of automated processing. It can be just a check that's run every time someone applies for a line of credit. That can be part of the controls that are run. So this is the kind of workload that our fraud solution is receiving. I thought I'd mentioned that I will not go too much into the detail of the graph, but if you're interested, you can go to our graph gist section on the Neo4j website. And if you go to the fraud detection category, you will find a detailed explanation of this example with the model and some of the queries, right? Okay, so back to our case. So we have these in place. We have this graph-based fraud detection solution in place, and there's another group of users. So there's probably managers that don't need to act upon every single case of fraud. They're not the analysts that need an operational view on the data. What they need is probably a more higher level view, and they say, hey, there's a lot of value in this graph. I want to know what these rings look like, what the people involved in fraud rings look like. I mean, what kind of customers are there? Could I combine this information with my CRM information and do some BI, some interesting analytics? And of course the answer is yes, and that's where the integration is going to come into place. So the kind of queries that these sort of users will be looking at is, for example, get me the list of fraudsters. And again, I'm not going to go into the details, but we can extend the cipher expression to include some kind of risk associated with the ring, which is basically a sum, is an aggregation of the credit card limits or the loans associated to the individuals in the fraud ring. So if we run that, that's returning a tabular structure, a data set, which is the kind of thing that these sort of users will want to be able to report and to analyze. So I can offer this view for integration with probably the CRM system. And one way of doing it, of course, you can there's a possibility of plugging directly some BI tool, and you can use for that the Tableau connector for Neo4j. But an interesting architecture is that the one that involves this integration middleware that we've been talking about, data virtualization. So what data virtualization does, as we're going to see, is well, it will wrap the source data and make it look as if it's all relational. And the interesting thing with that is that then you can combine as if they were building blocks, very much in the same way as you could combine relational tables, which is by doing joins. So let's see what that looks like. So we want to virtualize this view that I've just created in Neo4j. And the first thing I'll have to do is connect to the source, right? And that will be a very simple, filling in this wizard with the details, the connection details, where does the database live, which are my credentials, which is the driver that I want to use, and I'm going to use JDBC to do this. And once I've done that, I will be able to create a view. Hang on, let me see that here. In a very simple way. So basically, I will be passing the cipher, right, and eventually renaming the fields. But what I'm doing is I'm defining how to get this data set from the underlying data source. And now the interesting thing is that I can view this content, right? I can get it from Neo4j. And the interesting thing is that, well, I mean, you'll be surprised to see that what I'm doing is I'm running SQL against it, right? So of course, Neo4j doesn't understand SQL, but that's precisely what Data Virtuality is doing with the data virtualization layer. So it's exposing the data in a logical way as if it was a relational database. Interesting also to mention that there's no data movement at this point. So it's not ETL, so we have not copied the data, we have not extracted it out of Neo and copied into a data warehouse. We are retrieving it on demand. So as I run this query, Data Virtuality is pushing that query down to Neo4j, translating it into Cypher, and then retrieving the results and returning them. We're going to do exactly the same with the CRM system, right? So the CRM system is a relational source, and we will connect very much in the same way. So we will do it through JDBC. So we provide the connection details, and exactly in the same way, we're going to define a view with all the customer details, right? We can see what's inside there by running again a simple SQL query. We see that that's kind of information that you will get in a CRM system. So you get things like when were the customers last contacted by our marketing team, what's the marital status, what's the job, city, state, etc., etc. And they have a user ID is going to be the field that we're going to use for the join. But what we have now is two relational views that we can very easily combine together into another one by doing a single join. You can see it down here. So that will be the syntax that we would use in any relational database. So if you're familiar with it, you will see that it's quite straightforward. And again, this query, this view that we have created can be queried through SQL, and will return a joint view of the data coming both from Neo4j and from the marketing system. So we have all the information coming from the marketing or the CRM system, but it also contains the information about the size of the ring, where these individuals were involved, and what's the associated financial risk. Good. I thought I'd show this because it's quite interesting and very very great. It's a great explanation of what's going on. So I'll emphasize again on the fact that we're not copying data, we're not extracting it. It's a live on-demand view, and for that I'm going to show the query plan. So what the data virtualization layer is doing is realizing that the view that we're querying is actually composed of two other views that are joined together. So it's on demand breaking that query down in two that are sent. One of them, relational SQL query, sent to the CRM system, to the relational backend of it, and the other one is the graph query, the Cipher query that's sent to Neo. So it's doing this sort of query translation on the fly and aggregating the results again on demand and returning them as the result of the query, as we have seen, right? Pretty cool, right? So, and guess what? I mean, this view is something that we can expose in a quite natural way to BI tools, to any kind of consumer applications. But the case that we want to look at is that of BI. And well, here you can think of your favorite one, but I'm going to use Tableau for this example. And because this is a Windows machine, I'm going to access it through ODBC. When we list the available views, we will find our views folder, and within our views folder, we should have our fraudster view that we just created. So once we have it, I can drag it into into our dashboard here, and we immediately see the data. And again, this data has been pulled in live from the two underlying system, and it's a live connection. That's interesting because that will make our dashboard live. Remember that as we said before, new accounts are being provisioned, and I want to have a as close as possible to real-time view on it. Yeah, now we are in Tableau world, so we can start building our sheets in an easy way. So we have all the dimensions and all the measures. I'm not a Tableau expert, but we can, for example, very quickly report, convert into a dimension, and report on the number of rings by size, for example, right? So we can count the number of records. I'm not going to do anything very fancy, but there you go. So most of the rings are involved two fraudsters or two individuals, which are actually potentially not fraudsters, to be honest, but that's another question. But what I want to show is how straightforward and how agile is the process of connecting to the two underlying sources, combining them together, and offering them, presenting them as a single source for BI purposes. Keep in mind that this is a live view. This is a live view on our data, and well, the dashboard is going to be refreshed as the data changes in our sources. I'm not going to build it. What I'm going to do is show you a nicely pre-built one. That's just an example, but you can do all sorts of fancy things with these tools. And what we could, for example, present the rings by size, number of individuals involved in it, by average, and the financial risk associated with them, by regions, in this case by state, put it nicely on a map, or categorizing it according to different elements, for example, the financial risk or the number of cases, etc., etc. Good. I think that has kind of shown the idea that I wanted to share. Let me now go back to our slides. So I had a couple of backup just in case. So let me look at the takeaways. So what are the benefits of this type of solution? Well, graphs, of course, bring the intuitiveness of modeling data in a way that's much closer to the way we think about data. I mean, we don't have, if you're familiar with relational databases, traditionally, once you build your entity relationship model, once you build your your logical model, it has to be translated into tables and then eventually optimized, and that builds the gap between our understanding of the domain and what the data physically looks like actually, and that doesn't happen with the graph. I mean, the graph keeps that structure, and as we've seen briefly, not as much as I would have liked, we query the data pretty much in the same way as we think about it, as we whiteboard it.
So that brings this intuitiveness, which is key, and it's one of the feedbacks that we get from our users, and also the speed of development. The time to solution is reduced dramatically, and from the point of view of the development, but also from the point of view of the performance. I mean, the data can be queried and traversed in real-time scenarios like the one we've described today. Right. So on the data virtuality, I'll probably hand it over to you, Matthias.
Yeah, the benefits for data virtuality, of course, is the fast possibility to integrate your data, to have really connect new data sources in a matter of minutes. Whenever you need a new connection, a new connector to a system that no one has connected to yet, we can create this for you in some weeks or even in some days. So you're always on the safe side in terms of integrating new data, and you have the full capabilities of data management. Of course, metadata will be ingested into the server. You can model using the data, the metadata, and yeah, work really quickly with the data, explore stuff, throw it away, find new relations in your data, and be really agile in your data development.
Right. Yeah. So the intersection of the two will be obviously the agility that both bring into the construction of these solutions. Right. And well, probably also to give some ideas and some things we're currently exploring is how other possible integrations between the two technologies, or how they could be used in a different way. Probably you can talk the first two, Matthias, and I can describe the other two.
Yeah, sure. For the marketing data hub, this is actually something that a lot of our customers are doing, especially in e-commerce. They always have very nice views of one of their marketing channels, for example, but they don't have them combined, and they always need to find a way to put them together and do statistics. Which one is my marketing channel that gives me returns the most money for me, which I need to invest more, and this is something that they do with data virtuality a lot of times.
Right. Yeah. And the other two that we were exploring as well is, I mean, in this case that we've described today, we're using data virtuality as a layer on top of Neo in order to be the bridge between the backends and the BI analysis, the analysis tools. But data virtuality can also be used as a tool to unify the many sources that we want to bring into the graph. So kind of use it as a virtual ETL into Neo4j. So that's something that we're exploring currently. And one of our use cases, which is MDM, I mean, this idea of constructing a graph-based hub, where we bring into the graph the key elements to integrate data from different sources, but then access to the details through data virtualization is another interesting case that we are currently looking at and investigating. Right. So it definitely was not what we were planning, but anyway, we've got to this point, and we probably want to open it for questions. Greta, do we have any questions from attendees?
Yeah, we do. So attendees, now's the time. If you have any questions, go ahead and type those into the questions panel of your GoToWebinar control panel. We do have a few that have come in already. So attendees, go ahead and keep asking away, and I'll go ahead and start these questions. So we have one that's asking, how does it handle really large data sets? And I believe this was at a portion during the data virtuality segment, but maybe let's take a moment to answer both. How does data virtuality handle big data sets, and how does Neo handle big data sets? That might be interesting.
Okay, so let me go first. Of course, it's a very good question, and dealing with large data and real-time query, there's something that you think might not fit together. But there's for distributed queries, we have a lot of strategies to merge data, not by pulling all of it into our memory, but we can kind of stream it through. If you Google, for example, the merge join, hash joins, and so on, all these different joint strategies, they work in a way so that the joint data can be streamed through, and it doesn't need to go all into memory. And the other one is optimizing queries on the fly. So whenever a query is posed to us, we optimize the SQL to have it a very efficient distributed query queries, and the predicate pushdown, putting where statements and aggregations back to the data source, not doing this on our data virtuality server, is another aspect. And always the analytical storage, if you want to pre-compile results, just like you would in cubes, for example, you can do this as well. So any kind of aggregation can be pre-stored. It's not live data, but you can always do a hybrid approach between live data and historical data from the analytical database. So that's it from my side.
Good. Yeah, and probably just add that from Neo point of view, I mean, it's a database that scales very nicely. I mean, it can deal with billions of nodes and relationships, so it has very efficient storage. It does not have the rigidity, as I was describing before, of relational databases, where you have to describe what your data looks like up front and save the space and storage for these structures, regardless of the fact that you use them or not. So it's very efficient storage, and it can scale also to deal with very high throughput. So we can deal with large volumes of real-time queries, like the ones in the example that I was describing before.
Great. Okay, and then we have one question on, where exactly is the business logic set up for detecting the fraud? Is that all in the Cypher queries, or is that a combination of data virtuality and Cypher?
Right. Probably, or in this case, actually, the logic would live in Neo. So Neo, I mean, would have been much more clear if I would have had the chance to show it. But yeah, the fraud detection logic lives in Neo. So, and it's described in the form of graph patterns. So there's a number of potentially fraudulent patterns that we can describe using the Cypher query language, and these are being run against the graph database as data is provisioned. So we can think of course, we have to think of Neo4j as a real-time, constantly updated, alive dataset where accounts are constantly being provisioned, so new accounts appear in the graph, and new connections are being detected. So this logic is described in the form of Cypher queries. I mean, we probably won't go into the details today, but you can express them in multiple formats. I mean, you can also express it in Java through stored procedures, because Neo4j is an extendable platform. But in the example today, we express them through Cypher expressions, and they are detected as they appear in the graph and act upon, typically, I mean, in the form of trigger-like behavior. So whenever a particular fraud pattern is detected, an alarm is sent, or some individual is notified. So what data virtuality does is taking advantage of this logic that's in place to be able to extract that data and combine it with other data coming from other systems to provide a richer data set that can be consumed for the purpose of creating dashboards. But the logic in this case would live in Neo4j.
Wonderful. Okay, and then we have one person asking, so do these implementations make use of predictive analytics or machine learning?
Well, again, I'm going to take this one, Matthias. So there's two parts to the fraud detection. So one is the reactive one, if we want. So once we describe what a potential fraud structure looks like, we can automate the discovery of that pattern, so we can express it formally in Cypher. But then there's the other part, which is the discovery. I mean, given a large data set, what is fraud? I mean, in our case, we've described it as this idea of a fraud ring, individuals that share means of identification in a particular way that's unusual and that's therefore potentially fraudulent. But then there's the discovery part, and that's where more machine learning and where all these techniques can come into play. So that's not part of this demo, but that's of course something that graph representation will make will make, well, I wouldn't say very easy, but will make a number of techniques available. So things like structural analysis, like detection of clusters, detection of centrality, between the centrality. So there's a number of graph algorithms that can be applied to detect relevant structures in your data. Whether they're fraudulent or not, that's another thing. But I would say that all these ML initiatives would fall into this side of learning what fraud looks like from the data rather than automating the discovery of fraud.
Okay, great. All right, and so we have, I guess, a multi-part question. So have you integrated virtuality with a large ERP system like Oracle ERP that has large volumes of data? And then a second question is, how do you manage fields split between database options, especially where fields and field sets are asynchronous across the DBs?
Okay, so yeah, this is a question from my side. So for the first question, as I said, there's absolutely no limit on the data you want to connect, because we will not be ingesting the data. We will, if we connect using a virtualized connection to a large database, such as an SAP system, Oracle system, you name it, Hadoop clusters, for example, we also connect to. The data just remains in place. We keep the metadata on our server, so we constantly search for updated metadata, and whenever there's a query issued, we sort of ask the source system to get the data for us, and because of that, it doesn't matter how large the system is. It's always a matter of how complex your distributed queries are. So in the first place, for this Oracle ERP, a simple query to it would always just yield in an immediate result, so it's as fast as the Oracle database itself. For distributed queries, it kind of depends on how you optimize them, so how you do a distributed join over different systems, and this is where complexity comes into play. This is when where data virtuality really starts working and is filling its memory. So yes, we have been doing that, and it's always just a practical experience if you limit the tables somehow. So because especially Oracle tends to have a lot of let's say structural tables that don't really add much to the data. So if you limit that, you can connect it very well and work with it, as we've been doing. For the second question, for when data is spread across different tables and split across different tables, we see it in the way that the transaction just starts when you start reading, and this is the point in time, so to say, that is valid for the data. So for data split across different tables in one system, it would be part of the transaction for this to be well, a solid type of data. So that's it.
Okay, great. And can you convert existing ETL data to graph data without data virtuality? And if yes, how easy is it?
Yeah, absolutely. I mean, you can. I mean, there's a number of ways in which you can ingest data into the graph from any kind of source. I mean, we see that most of the times that comes from relational, from tabular structures, and there's that can be done through Cypher again. So there's an instruction called load CSV where we can and a number of procedures to access tabular relational data. And basically define through Cypher how this translation, how this mapping is supposed to happen. So how every record is broken down into bits to create nodes and connect them between each other. So I would recommend you go to the Neo4j website, because there's plenty of material around that. So you can ingest data from relational, but also from hierarchical, from JSON based, from all sorts of into Neo in a number of ways. For large data ingestions, there's also batch-based approaches. But yeah, I mean, there's no need for any. I mean, it can be done through standard ETL tools. Or data virtualization, data virtuality would be an option, of course, which is one of the cases that I said at the end that we were exploring. but it can be done just scripting it in Cypher, which is a very easy and intuitive way to do it.
Okay, great. And then I think our last question, is Data Virtuality available for download, or where can we find more tutorials about it?
There's a lot of material on our website, so I did some videos actually that show a complete use cases for example, combining historical data with real-time data. And of course, if you just approach us and just get in contact with us, we can provide, for example, a 1-month demo server for you, and this can be arranged, no problem at all.
Okay, great. Well, thank you both for this wonderful presentation, and attendees, just a reminder, we will be sending out the slides and a recording of this presentation most likely tomorrow. So if you've registered for this webinar, which you all have, you'll get the email with both the slides and the recording. But please feel free to reach out to us should you have any questions. You can reach us, on the Neo4j website makes it pretty easy to get in contact with us, or tweet at us at Neo4j. And yeah, thank you all so much for joining.
Thanks from my side as well. Bye, everyone.
Cheers. Bye. Thank you.